For this next video, we're going to be creating some graphs based on the data that we had in our previous practice set. We're also going to run a Shapiro-Wilk normality test on all of the variables in the data set in SPSS. For future activities, you guys can choose to create graphs either in Excel or SPSS. I think that graphs are easier to edit in Excel. However, SPSS does have some advantages for different things that you can do on graphs that might be a little bit more difficult or take more steps in Excel. So we're going to start on practice 2, or the sheet practice 2, and we're going to make our graphs in Excel first. So let's look at our mass data. So I'm going to highlight all of the data for mass. I'm going to insert. And the first graph we're going to make is a histogram, which we've made in activity 1 prior to this. So first things first, let's label. For these graphs, I honestly think it's fine if you just put the variable name as a chart title. In research settings, probably not the greatest chart title because it doesn't describe what's in the graph super well, but we just can put mass. Remember that you'll want to add axes titles for both the primary vertical and horizontal axis. Reminder that in histograms, the vertical axis represents the frequency at which certain values in your distribution occur. And then the bottom axis, or the x-axis, is just going to be the variable that you've plotted. So in this case, it's mass with our units of measurement in kilograms. If you are in Windows and you double-click on the x-axis, that will bring up your bin adjustment toolbar. Given I'm in Mac, I'm going to double-click on the bins, and this will pull up my formatting toolbar. So for mass, remember that we can adjust how our bins are displayed either based on bin width, so how big the interval is, or we can adjust it based on the number of bins. And now that we have a sense of what a normal curve looks like and what it indicates, right, now we can actually look at histograms with a closer eye to use them to evaluate shape. So if I just put my bins, or number of bins, to 3, we can see that this visualizes the data differently from 5 bins, different from 10 bins, right? So in either case, when we've already calculated our skewness, our z-skewness and z-kurtosis, and we know that based on those values, mass was relatively normal. We also had our SPSS output that showed mass in a histogram with a normality curve or a normal curve kind of overlaid on top, and we can see that generally our data match a normal curve. Okay, so we can fairly see that this histogram matches what we've kind of investigated both with numbers and with plots in SPSS, at least the plots that we've tried in SPSS. Okay, so you can play around. I think 5 bins probably represents this data the best, so we can keep it at 5. The other chart I wanted to show you guys how to use, so we reselect the mass data, is a box plot. And box plots are helpful in identifying outliers sometimes. So again, I'm going to label this one mass, just so I don't get it confused. And then my axes Really, the x-axis is not super necessary to have unless you have a multi-series or multiple series being plotted, and we'll show an example of that in the next practice video. But in a box plot, instead of your units being on the x-axis, your units are now on the y-axis. So y now indicates mass in kilograms. And if we look at this box plot, or also commonly called the box and whisker plot, it's based on our quartiles. So the first side of the box here is, well, actually, if we're going from small to large, right, or the low end of our distribution to the higher end of our distribution, right, so looking at this, it would be similar. This side of our box and whisker plot is the same as looking at this side of our histogram. And as we move up, it would be similar to moving across our histogram. So we can look at this by the first line or the edge of our box. That is considered Q1, or our 25th percentile. The middle line, which kind of lies just underneath our graph lines here. If I remove these, you can kind of see it's darkened and it's not a continuation of the graph lines. This line represents the 50th percentile, or Q2, so Q1, Q2, and then Q3 is our 75th percentile. So this shaded box represents the middle 50% of our distribution. The X in the center represents where the mean is located. And ideally, if we have normally distributed data, our mean value should be very close to that 50th percentile. These whiskers are created by using the IQR method. So this is Q3 plus 1.5 times the interquartile range. This whisker would be Q1 minus 1.5 times the interquartile range. And then the cool thing about box and whisker plots is that if you have an outlier, it will show up on the outside of our data. So if you recall from practice 1, we did our interquartile method down at the bottom, and we were able to identify different outliers for different variables. Okay, so let's try making a box and whisker plot for height, since that had an outlier, and we'll see how it compares, or at least give you a visualization of how outliers are presented in this type of plot. So we've created the plot. I'll move this over. And this is going to be our height data in centimeters. Apparently I can't spell. And then same thing, you'll add your primary vertical axis label. Come on, there we go. Which is going to be height in centimeters. Okay, again, x-axis in this situation isn't super important, so honestly we could probably leave these out for these plots. But you can see there's an outlier that's below the mean, or below the lower bound of our IQR method, or lower bound, yeah, from our IQR method. And if I hover over this point, you can see that the value is 168.7. If we go back to practice 1 and we look at our height data, we had identified an outlier below the lower bound. Remember, this top row was lower bound, bottom row was for the upper bound. And then we applied our conditional formatting to the height column and found that the outlier that flagged here was 168.7. So our graphs match. Right? So using a box and whisker plot essentially identifies outliers in the same way that the interquartile range method identifies outliers, which is pretty cool. Okay. So that's pretty much it for Excel. I'll let you guys practice plotting histograms and box and whisker plots for the rest of the variables, just for good practice. And then in SPSS, we have several different options on generating graphs, and I have kind of outlined those in this bottom area. So we've already done one way using a frequencies analysis. The other way that I think gives us the most graphs within one fell swoop is using an explore analysis, which conveniently is tied to our Shapiro-Wilk test for normality. So we're kind of going to do these two things at the same time, pretty much following the steps outlined in point 3 under practice 2. There are other graphing options under legacy dialogues and compare groups. I'll show those to you briefly in this video, but I think any graphs that you need to make can easily be done in the explore section. So let's shift to our data set in SPSS. This is the same data set that we had copied over for practice 1 part 2. So it's already set up the way that it should be. If we want to run an explore analysis to get our normality tests, we go to Analyze, Descriptive Statistics, and Explore. This will bring up a dependent list box. We can literally put any and or all of these variables into the dependent list. So I'm going to choose, let's do bench 1RM and VO2. The factor list, we're going to keep this box blank for now, but if you had an independent variable, you could add that to this box. And that would essentially help split up your dependent variables based on how they are classified with your independent variable labels. We're going to choose the option for statistics. This allows you to identify descriptives. You can identify outliers or percentiles. I'm going to keep those unchecked for now. Whoops. And click continue. Under plots, for box plots, let's keep factor levels together. We can do a descriptive plot as a histogram. Stem and leaf plots also show trends of normality, but they're kind of like a sideways histogram with numbers instead. We don't really look at those in this class, so we can skip that box, but we definitely want to look at a histogram. And then we can also generate normality plots with tests. Checking this box ensures that you get the Shapiro-Wilk test with its p-value. It also will generate QQ plots, which we don't analyze in this class, but I can talk about them in this video. And then that's pretty much all you want to choose in the plots section. For our options, we keep this the way it is as a default setting, and then bootstrapping we don't deal with in this class. For the last bit, you can choose to either display the descriptive statistics or plots, or you can do both. We're going to do both for now. And we can click OK. This will pull up our output, and you will see that once it runs through everything, we now have our explore test added to our output. So I'm going to change the name of this to practice 2. That way we can easily navigate through everything. We can see at the top, right, how many were in our sample size. There were 0 cases missing, so we're not, we haven't lost any data. Our descriptive statistics will show up for both of the variables that we inserted. So we have mean, median, variance, any of this good stuff. Okay. Again, for skewness and kurtosis, there is both the statistic, so this is the sample skewness and sample kurtosis, and then you'll see this second column for standard error. So if we were in, or if we were trying to calculate or assess distribution shape based on z-scores for skewness and kurtosis, again, you would need to divide the statistic by the standard error in order to get the z-score in order to evaluate your distribution shape if you were using the explore function for these particular calculations. The cool thing about the explore calculations is that it includes an interquartile range, which was not included in the frequencies analysis or in the means analysis. So if you ever didn't want to do the work for that one, you have it in this command option. As we scroll down, we see our tests for normality. Each row is organized by the variable that was put into the test. Reminder that the Kolmogorov-Smirnov normality test isn't one that we necessarily look at for this class, but you can see the differences between our sig column, which, side note, anytime you see sig in SPSS, that indicates a p-value. So if you recall from the lecture, for the Shapiro-Wilk test, we want a p-value that's greater than 0.05. And we'll get into talking about p-values and hypothesis testing next class. But basically what we're doing is we have a null hypothesis and a research hypothesis for any given p-value. And our null hypothesis usually argues that there's no difference, there's no effect, there's no relationship, that type of thing. In this case, we are saying that the sample distribution is equal to or represents a normal distribution. So if we have a p-value greater than 0.05, then we accept that our sample has a normal distribution. If we have a p-value less than 0.05, then that means that our sample is not normal. In which case, we might want to look at z-scores for skewness and kurtosis to understand why it's not normal. Or we could look at box plots or histograms or do the IQR method to figure out if we have any outliers in our data set. Maybe somebody input data wrong, or you just have a wild card in your sample. Okay. So in this case, both Bench 1RM and VO2 tests have been flagged as normal, which we would expect because if we scroll down to our histogram, our sample size is 100, which should be large enough to help us kind of make the central limit theorem come to fruition, right? So central limit theorem again says that if we have a sample that's large enough, our data should be normally distributed, which we can see generally we've got this bell-shaped curve going for us here. So that's for bench. Continuing down, we have QQ plots, which are normality plots, and basically what happens is you create a model, or you don't do it, SPSS creates a model, and then it puts all of your data points along this model, and basically the more lined up your dots are with the line, the more normal your data are. If they create an S shape, that indicates skewness. If they go above or generally below the line, that is kind of a flag for kurtosis. Again, we don't really mess with QQ plots, but if you're interested in what it means, that's what it means. We definitely don't look at detrended normal QQ plots, so we can skip over that. Then you can see our box and whisker plot or a box plot for bench, right? And the SPSS program does essentially the same thing that our Excel box plots do, and that it shows which values have been flagged as outliers. So if we went back to Excel, this was for bench 1RM, and we inserted a box plot, you can see we generally get something kind of similar. What I'll do to blow this up a little bit more is just to change the minimum value to, let's say, 80. Okay, and we can see that we've got a point out here and a point out here. Right, so in this one we're saying that 164 is an outlier and 100 is an outlier. This one has identified 2 outliers, one above and one below. If we look at our data from practice 1, using the IQR method, there should have been 2 outliers above and below our defined bounds using the IQR method. If we go to SPSS, right, we can see that we've identified 1 outlier above the upper bound and 2 outliers below the lower bound. You can see in SPSS that these values next to these outliers are not in the units of the bench 1RM data. What they actually represent is the number that is assigned to the value. So essentially it would be similar to saying subject number 3 was an outlier, subject 37 was an outlier, and subject 18 was an outlier. We could check this by going back to our data, right? And we can see if we count down, subject 3 was an outlier, subject 13 was an outlier but was not picked up by SPSS. Subject 18 was an outlier that was picked up by SPSS. And then if you recall, there was a 4th one, and look at that, subject 37. Okay, and I'm just referencing the count function for the subject value. We could also look at this in the data view over here and see for bench, right, this value would have been an outlier for 3, 18, and 37. I just chose Excel because we had them highlighted in red, so it was a little bit easier to view. So those were examples of graphs that automatically come in different analyses in SPSS. If we wanted to create a graph from scratch, we can use the chart builder. And in here we can see our list of variables and a list of different graphs to choose from. So let's say we wanted to make a histogram. All we have to do is drag and drop any of these elements into this chart builder area. Now for a histogram, our x-axis represents the variable that we have measured, and the y-axis represents the frequency. So let's say that I wanted to graph my VO2 values. I would just drag and drop those into the x-axis, and my histogram should automatically recognize that the y-axis is a frequency. Once all of your elements are included, we can click OK, and then we can see the histogram. Now, similar to our histograms in Excel, we can adjust the number of bins that are shown. If I go back to the chart builder, I can set parameters and set a custom number of intervals. So let's say I only wanted 8 bins. I could click continue, OK, And then I get a chart that's regenerated with only 1, 2, 3, 4, 5, 6, 7, 8 bins. If I double click on the graph, I can alter any of the X or Y axis labels. I can also alter the title. So these would kind of be similar in how we would do it in Excel. When you're done editing any of those elements, you just click the exit button and it should save any of the changes you've made. If you've made a graph that you don't want to keep, all you have to do is click on the yellow kind of notebook icon, and then you can just cut it from your output. We could similarly do something like this by making a box plot. For box plots, as we did in Excel, the x-axis doesn't really have anything on it. The y-axis is going to have our variable of interest. So if I wanted to do a box plot of GPA, I can click OK, and then I can see my box. And you'll note any outliers that exist will be listed there. Again, if you wanted to change any of your variable or any of your chart contents, you can just double click on the graph. I notice this whisker is a little bit close to the bottom of the graph. So if I wanted to change my y-axis labels, I could double click on those, go to scale, and then this would be similar to our axis formatting toolbar that we have in Excel. So maybe instead of the minimum being 3, I want it to be 2.5. I can click apply, and then I see those changes have been made on the graph. So you can adjust these to whatever you think represents the data the best, as long as your entire chart is showing. And then again, you can click OK. Sometimes when we have multiple groups in a variable, such as a nominal variable, we might want to plot like boxes and whiskers of each category next to one another for comparison. Because we don't have any nominal variables in this data set, we can't really do that example, but I can surely show you that example in the next video.